Hello, welcome back. We're going into Chapter 9, Slope Fields and Separable Differential Equations. This is a little bit of a catch up here to, well, not catch up, I mean help you get ahead for when you take differential equations, because the first couple chapters of a differential equations course are pretty difficult, and so the newer calculus books actually introduce some differential equations within the Calc 2 or Calc 3 curriculum. And in our case, we're doing this in Calc 2 because we can. So this is so it help you get a little bit of a head start here for your differential equations class. And so when it came to differential equations, I took a sentence out of one of my favorite differential equations books, and that's William Boyce's Elementary Differential Equations and Boundary Value Problems. And I'll read this to you. They require the determination of a function satisfying an equation containing one or more derivatives of the unknown function. And seems a bit vague at first here, and that's perfectly fine. That's what examples are for. And so, well, we'll talk through this, through these first order differential equations. First order because they have only one derivative. And what's shown here in this line that begins with the letter F is not necessarily a first order differential equation. Notice that we have the first derivative, a second derivative, and an nth derivative. So the order is really the highest derivative involved. And so a first order differential equation is only going to have one derivative. That's going to be equal to dy dx. But the catch is that this is going to be equal to some function containing both an x and a y. So we have a derivative and an x and a y all in the same place. That's a differential equation. So imagine, let's say you have y prime equals x times y. And you have to solve for y. Well, you can't just, let me draw this out here. And so you have, let's say y prime is equal to x times y. Solving this differential equation is a little bit more complicated than just saying y prime over x. No, that doesn't cut it. This is it's going to actually involve finding a function y that satisfies this requirement, that if you substitute in the y and then multiply it times x, it would be equal to y's derivative. And that's what a differential equation is. And they're quite a learning curve, but once you get to understanding them, then they suddenly become not nearly as difficult. So here's a slight but very exact rephrasing of the first order one on the previous slide. I changed the y prime into this dy dx form, and then we have a y variable here, and we have two other things, a p of x and a g of x. These can be anything. They don't necessarily even have to depend on x. They can be constants or they can be functions of x. And this would be a first order differential equation of this form. And for example, what if p of x is equal to 2 of x and g of x is equal to 3? This expression y prime plus 2xy equals 3 is a differential equation. And you would go about finding a function y that's equal to something such that if you multiply it times 2x and you add it to its derivative, y's derivative, everything would just cancel out and leave you with 3. Well, I'm going to step you through this process. And the cool thing is what you do it once, you can do it 1,000 times. And not entirely intuitive at first, because right at this point, this is one of those problems that looks really difficult, but that's because you haven't seen a solution yet. But before we go into this, we probably should just test a few solutions. Just test if a possible y value, a y function, is a solution to a differential equation or not. So we have this example. I included at the top here the template for a first order linear differential equation. And in this case, p of x is equal to 1/2 and g of x is equal to 3/2. We end up with dy dx equals y over 2 equals 3/2. I decided to use x for this, and because graphing works a bit more naturally like that, and to give you a hint, we will see a graph of this later on. So I chose x instead of a t. And in fact, I didn't notice this. This is mismatched types here. So we have this function. It's y prime plus y over 2 equals 3/2. And so this can potentially have an infinite number of solutions. But one solution to this equation is given right here. 3 plus 7 times e to negative x over 2. Is this a solution? Well, we can substitute it back in. We'd also have to take the derivative and substitute it back in. The derivative of this, let's go to a nice blue color here, because blue is a great color for derivative. Y prime, derivative of 3 is equal to 0. And then we have 7 times the derivative of e to negative x over 2. That's going to be times negative 1/2 of e to negative x over 2. So the derivative is equal to 7/2, negative 7/2 e to negative x over 2. I didn't use a nice blue color for this derivative. It's in red. And so what you basically do to test is take the derivative and then substitute the y in, substitute the y prime in. And with a little bit of algebra, get them to simplify. If the equality does not work, it is not a solution. However, if they balance out, it is a solution. So let's break this 3 plus 7 e to the negative x over 2 into two separate fractions, like 3/2 and a 7/2. And so now notice something here. We've got 3/2 here. We have a 3/2 here. We also have everything else is multiplied by e to negative x over 2. We have a positive 7/2. We have a negative 7/2. So these 7/2 are going to add up and cancel out. These are going to cancel as well because they're multiplied by it. It would be multiplied by 0. And we're left with 3/2 equals 3/2. This is definitely true. So it means that this actually was a valid solution. And up here is our solution, by the way. And notice that it has a 7 in it. The derivative also has a 7, but it didn't really matter because they added up to 0. So actually, the number 7 could have been any number. It's one of those things that it didn't really matter. And so what it tells us is that that this could have just as well been any constant c, and which I wrote here as a c. Remember, I said these can have an infinite number of solutions, and in this case, it did. It has. You can choose any number for c, and you'll have a solution to it. And you're probably wondering, or maybe worrying, how did I come up with all this 3 plus e to the negative x over 2 as a solution? Well, it takes doing this blind is really, really difficult. However, it's also a very famous problem of which is demonstrated in practically every differential equations textbook. And I'm going to recite the steps to you here, so you'll know what they are. That's what my example B is. So the solution. So this is how the solution will be found. To find the solution to a differential equation that you're not familiar with, you really have to know your derivatives and integrals really, really well. In the sense that you'd have to recognize how you can turn your function into an integral that can be simplified. And this one, to solve these, for example, is going to be based on the integral of du over u, which is equal to the natural log. And if you can recognize that you can put it into that form, this would help. If, for example, if this was a y square, that you might think that you could do maybe a power rule integral to solve this, for example. And anyway, but that's deviating too far from our first order linear differential equations. In this case, we're going to be using the integral of du over u. How do I know that? Because this is actually a very famous type of differential equation, so I've seen it a lot. And somebody showed this to me the same way I'm showing it to you now. So keep track of this integral. You'll be seeing it soon. And so to make it look like du over u, you need to get the y prime over the y. And so we have to do a little bit of algebraic rearrangement. And so bring the y over to the other side because we're going to be dividing it under eventually. And now those two terms are divided by 2, so you can put those under a common denominator of 2. And now divide both sides by 3 minus y. And there you have it. You have the y underneath the y prime. And in fact, if you multiply both sides by -1, then you can use the rule of this integral of du over u. So multiply both sides by -1. And did I do that? Did I make a mistake in this? Did my slides get out of order? Hello, welcome back. We're going into chapter 9 here, and this is a chapter to help you prepare for differential equations, because over the past few years a lot of students have been having trouble with the beginnings of their differential equations courses. So this is something to help you out, to give you a little bit of advance warning, a little bit of preparedness to when we get to that. And that is why that this has been included in the Calculus 2 and Calculus 3 books nowadays. It's in by popular demand of the math professors. And so this is a introduction to differential equations. In this case, this is going to be first order linear differential equations that we'll be seeing. So differential equations, I'm going to take a sentence out of one of my favorite books on the topic. That's written by William Boyce, his book, Elementary Differential Equations and Boundary Value Problems. It is an authoritative book on the subject of differential equations, and there's a good chance that you may actually see this as a textbook for your class. He defines it as these problems that require the determination of a function satisfying an equation containing one or more derivatives of the unknown function. That is what a differential equation is. And so let's take a look at a few of them. Here's a general case of a differential equation. These aren't necessarily first order. This first statement here definitely isn't. But this is sort of a template for what a differential equation is. A function that depends on an x, a y of x. So there's an x and y in this function. There's also a y prime. There may be a y double prime for a second order differential equation, or an nth order differential equation. And this is a definition of what these are, differential equations. And so a first order only has just one derivative. It would be restricted to just these. And we could write it in the form of y equals dy dx, so the same thing really, is equal to a function with an x and a y term in it. So it's a function of x and y returning a value that just happens, or in this case it's returning a different function. It's not returning a value, it's returning a function that happens to be equal to y's derivative. And that's sounds a little bit screwy, but that's how they are. But we'll see a few examples of them. And so when f depends on y, we can write our equations in the form here. And this is a standard form actually that's pretty popular. You have your p of x, which is multiplied by y. You have your g of x that isn't, and you have the derivative of y. This is the template for what a first order differential equation is. And so there's this term that's multiplied by y, and there's also a term that isn't, the g of x. And so, for example, what if p of x is equal to 2x and g of x is equal to 3? Then we get this differential equation of y prime equals 2 times x times y is equal to 3. And now the trick is to find out, okay, what is y equal to? Well, it's not as simple as doing something like saying y equals the 3 minus y prime over 2x. A math professor would laugh at you if you did that. And I would admit it is sort of funny to solve for y, but that's not what we're doing. I did that to my differential equations teacher, by the way, when I was in college. But he asked me to solve it on the board. That's what he got. So anyway, what we need to find is a function y that we can substitute in here, where if you add its derivative, the everything cancels out algebraically and leaves us with a 3. That's what you get as the reward for solving a differential equation. And let's look at a real example of this. Let's say p of x is equal to 1/2 and g of x is equal to 3/2. And I'll state right now this is supposed to be an x and not a t, dy dx. And now this is so this would give us a differential equation of the form of y prime plus y over 2 equals 3/2. There it is, differential equation. And now as far as solving these, we'll get to that. But the good news is that this type of differential equation is very famous. And it's also not a particularly complicated one, in the sense that when you figure out how to solve one, you can solve them all, basically. The method of which it's done is highly standardized, and it is in practically every differential equations textbook as a teaching example. And so we have this. So this is not anything that's really unique to this video or to this class, but is actually a famous group of math problems. So here we are. We've defined this differential equation, and so it can have these can potentially have an infinite number of solutions. In fact, these are infinite. One of the solutions to this equation is given right here. The y equals 3 plus 7 times e to the power of negative x over 2. And how would we check that this is a solution? Well, you take this function y and you substitute it in. You would also need to find a derivative too and substitute that in as well. And so this derivative is going to be 7 times e to the negative x over 2. And now the derivative of x over 2 is going to be negative 1/2. So this is going to be times a negative 1/2. And so it's going to be negative 7/2 over 2. The derivative of 3 is 0. So you're going to have negative 1/2, negative 7/2 times e to negative x over 2 for your derivative. You substitute that in. I chose red. Red is a good derivative color. And when you perform this, you would want to see that these do cancel out. And so, and here we are. Let's test it. So in black is the differential equation we started with. We have our hypothesized solution in green and a derivative in a nice red, sort of dark red color, and we substitute them in. And so I color-coded these to show how they are substituted. And we'll have to do a little bit of algebraic simplification on these to try to get things to cancel out. One thing I did is I broke apart this into two fractions, 3/2 plus 7/2 e to negative x over 2. And now notice something that we have the positive 3/2 here. We have a positive 3/2 over here. We also have a positive 7/2 times exponential and a negative 7/2 times exponential. And basically these are equal because the negative 7/2 and the positive 7/2 add up to 0. It leaves us with 3/2 equals 3/2, which is true. So it is true when you substitute that equation in to this differential equation, that you get that it's true. It is a solution. So that's how you test them. You take your function y, you take the derivative, and you substitute the 2 in and see what you get. If they're equal, it's a solution. If they're not equal, it isn't a solution. And so that's all there is to it. Now you might be wondering that e to the negative x over 2 is certainly a crazy function to have as a solution. You're probably wondering where on earth that came from, or maybe you're worried about where that came from because you might be a little bit afraid of the math done to get to that. And I should say that the steps to finding solutions require you to be really on top of your integrals and derivatives. And however, this is a very famous type of problem, and the procedure is listed in practically every differential equations textbook. So this isn't really magic except to the first person who ever did this calculation was no doubt very highly regarded at discovering this method. And then once you learn this method, you can reproduce it in as many scenarios as you want. In fact, I'm going to show you 100 or 200 different solutions before this video is over, and you're probably thinking like, holy cow. But I have a special way. And so this solution, you might have noticed this. The number 7, there was a number 7 in the solution, but there wasn't a number 7 in the differential equation. And it could have actually been any number. And because the e to the x terms that had the 7 in it canceled out. So this one actually had an infinite number of solutions, and so they're often written like this. This type of solution is called a general solution, and you'll see that again soon. Now let's take a look at how we get something like this plus 7 e to negative x over 2. So yes, you have to be pretty strong on your integrals. This one actually uses the rule of the integral of du over u being equal to the natural log of u's absolute value. And now notice that we've got this natural log, and our answer had an e to it. Well, that's where the e came from. It's actually a side effect of this natural log. And so we want to we want to get this differential equation into the form of where we have something like y prime over a y, perhaps, just like this du over u, and then we can take the integral of it and solve for y. So algebraically, we need to get this y in the denominator. And here's a pretty straightforward method of getting there. I brought the y over 2 to the other side and combined the denominators and divided by 3 minus y. And I end up with y prime over 3 minus y equals 1/2. And we're pretty close to it. We're not quite there yet because we have a negative y and a positive y prime on top and a positive 3. It's sort of awkward. In fact, it's quite awkward because we are wanting to deal with a natural log, and we might end up with a natural log of a negative number. So we will have to multiply both sides by -1. And then we can write this up as like this derivative. We have So we end up with y prime over y minus 3 to negative 1/2. And that looks like our derivative of du over u. And that's so basically you would if you took the integral of both sides, you would find that this is that you would get this integral. Well, you'll see that on the next slide here. I'm trying to talk over what I haven't written yet. And so basically, these are equivalent. The derivative of natural log of y minus 3 is equal to this. And so now let's take the integral of both sides. The integral here, the integral here. And now these integrals and this derivative are going to cancel out. They are going to go away. And now this integral of negative 1/2 is going to be negative 1/2 x. And that's where this x comes from. Because we are integrating with respect to x over here. And so we have natural log of y minus 3 equals negative 1/2 x plus c. And now remember how when we integrate and we with an indefinite integral and we have this variable c, or not a variable, I mean this constant c that we keep on because we have an infinite number of integrals depending on what c is equal to. Well, remember we had an infinite number of solutions to this differential equation? This c is critical to coming up with this answer, so you don't ever forget this c, because if you do, you're not going to find a solution, or you're not going to find all of them. And so we're almost there. We have to solve for y, and to do that we're going to have to take the exponential of both sides, e to the natural log, e to negative 1/2 x. Oh, look at that, e to the negative 1/2 x. Don't you remember that somewhere? Don't forget we have to do e to the c. That's important, very important. Take the exponential of everything. And so we end up with y minus 3. This suddenly just got to be fairly easy to solve for y. We have e to the c and e to negative x over 2. It turns out that by rules of exponentials, they can be combined like this, the sum rule of exponentials. And what we'll do is we'll reassign e to the c power is equal to lowercase c. You solve for y, you end up with this. Notice this looks familiar? It's just like the solution to the differential equation we did earlier, except in that case, c was equal to 7. So that when you have the letter c in there, it covers where c can be any number. This covers the entire family of solutions, and it's called the general solution. And when you come up with a initial condition, such as like y of 0 equals 0, for example, you would have to solve to find out what c is equal to, and that gives you the particular solution. We will see that. And so we have this general solution. So let's do this initial value. Let's say y of 0 equals 7. And I just thought I'd make up the number 7. There's no connection to the number 7 at all anywhere else. I just made up that number just now. And you substitute it in. So if this y of 0 has to be equal to 7, well, that's why it's equal to 7 here. And now this is c times e to the 0 because 0 is the input. And so negative 0 over 2 is 0. E to the 0 happens to be a really nice number because it's equal to 1. So this is 1. We can just sort of scratch it away because we're left with 7 equals 3 plus c. What would c have to be equal to? It'd have to be equal to 4. And so given the restriction of this initial condition, as they call that in the initial condition, it's a restriction that forces your c to take a value. In this case, this is an equation that represents this curve. This curve passes through y equals 7 for when x equals 0. So that's one of our curves. Now, depending on how you change, make up guesses for 7 or even 0, it wouldn't cancel out nicely, so you'd end up with decimals numbers for this, but you'd end up with an infinite number of solutions. And so as you take these solutions and graph them, you'll see a pattern of curves drawn all over your graph. But there's sort of something of a pattern to how they look, and that pattern is called a slope field. And so we take this, so we choose different x's and zeros and imagine them being graphed, you'll get a slope field. And this is what one looks like for this differential equation. So we chose one that came through 7. If we sort of imagine that if we had more and more of these points, we would see like the line going through here, comes out and sort of levels off. And finally it begins to approach the line, the y equals 3 right here. Eventually gets very close to that as x becomes large. And so this is what I meant earlier when I said you'll be graphing hundreds of these. This is it. These are little segments of all the different graphs of initial conditions for when you, like, say you have the 7 and this approximately negative 2.5. That's a section of that curve. If you have an adjacent one, it could be very, very close to it, very close to these other curves, and it'll end up crossing the y-axis somewhere and continue out until it becomes very large and approaches 3. This is what it looks like when you superimpose many, many graphs on top of each other in the form of little segments. And so you'll see this general path of functions starting at a certain point and then sort of pushing down closer to y equals 3 as it increases. So that's what's pretty cool. You notice, you might think this looks like little pieces of metal filings underneath a magnet. Well, guess what? Magnetic fields are modeled as differential equations. So we never see the lines of iron filings, pieces or iron dust being moved around on a piece of paper due to a magnet. You're seeing the differential equation field lines, basically. In fact, also in the study of electromagnetics, those are also called field lines. It's the same thing. You're actually visualizing them. This viewer actually came from mathscoop.com. I basically told it the differential equation y prime. In fact, the y prime is given to you. You have to enter into the box. What I entered here was y minus 2 plus 3 over 2. And it produced this for me. That's it. It's automatic. And so you shouldn't have to do the 5 minutes of math just to find one of these every one of these curves. Each of these being representative of a line. You shouldn't have to do that. There's these tools that help. One last example, just sort of a review. I didn't really have a better place to put this, so I put it at the end. So just another example of this. For the differential equation given here, show that e to the negative x is a solution. So this is sort of fast. Y prime is equal to negative e to negative x. You substitute this y prime here. You substitute this y here, and test that's equal to this e to the x. Next, I'm going to have to circle this correctly. Yeah, got it. So take the y function and its derivative and substitute them in. You get negative 2, positive 3. So that's going to be 3 minus 2 is equal to 1. 1 e to the x. And that's what you got here. So this equality is true. Yes, it is a solution. So that's how it's done. Differential equations. You've seen it now. So have fun with it. The homeworks are not going to be nearly as involved as this. I'll see you in class when we talk about this.